Okay, so the title of my talk is, it's really a bird's eye view, but in key areas I'm going to be specific. How Metasurface Flat Optic is allowing to go from components such as metalenses to manufacturing processes and to actually systems. Okay, so this is the outline, and I want to cover the big picture first, some of the design principle, talk about the nanofabrication technology, which is absolutely critical going from the laboratory to mass manufacturing. I want to talk in particular about the metalenses. An important topic that is coming more and more is multifunctional metasurfaces. While metasurfaces, I would say that on one end can replace in many instances standard optical component with optics which is thinner, less bulk, less aberration. I believe the real promise is in doing functions in a much less complex way than traditional fine, moreover, probably create entirely new function, and that's really quite exciting. I'm going to talk in particular about very interesting recent work on application to light-emitting diodes such as OLEDs, and finally meta cameras. So this is a big picture. I wrote a short review here a few years ago. So we all know that they provide arbitrary control of the wavefront. They enable flat optics. We said about multifunctionality. There is a wide range of components. But really what got us, me and my group, very excited, we realized at some point, we can make this stuff with the deep UV lithography. So the vision is that in the future, and it's just starting, I will give you one example which is compelling. Foundries will manufacture camera sensor and lenses using the same technology as integrated circuits, so CMOS compatible flat optics. The largest market is in generally sensor. There's also cameras, of course. One example, in fact, this was announced recently by Metalens Inc. Lens in cell phone camera modules will be replaced by metalenses fabricated by deep UV lithography. An example, which is happening in real time, moving towards dot projectors for face recognition and depth sensing, which will go directly into the cell phone. We're not talking 10 years. What I see on a horizon of 3 to 5 years. Displays, wearable optics, it's still kind of in the making. And this is not going to be about the science, this talk about the technology, but you can create arbitrary vector beam. I just gave a talk earlier this morning on structural light and structural dark. I want to stress, and this is something as a physicist, it's been hard for me to accept, but if the tool is useful, let's go for it. The importance of inverse design using artificial intelligence, basically. So particularly interesting co-design of hardware, so it's an unstoppable trend. It will make optics much more powerful and easier to design and do some real discoveries. This is just a very abbreviated history of the electric flat optics that I got courtesy of Mark Brongesma. The work starts, of course, with the shell gratings back in the 70s. This is not digital. There was earlier work by Philippe Lalande and Paul Clavel about making Blaze binary gratings. The work moved on with work by the Hausmann group. And this is work by the Brongesma group, the electric metasurfaces. These are high-performance metalenses that really put, I believe it's fair to say, metalenses on the roadmap to influence big time the future markets. There are other very interesting applications, of course, and non-local metasurfaces, dynamic metasurfaces, and the promises here, we talked already about it, so let me move to the next. The conventional lens manufacturing is so successful that we forget how complex it is and the bulk. It doesn't matter where you have a complex objective. As you can see here, let me use my spotlight here. Okay, this, or you in a cell phone, you have to use multiple materials, the alignment is critical, very critical, and it adds cost. And these machines, you know, for example, for aligning, this is a commercial machine, cost millions of dollars. Plus the control of aberration. Again, the technology is successful, but we can do much better with flat optics by going towards a thinner, better control of aberration, less bulk, and more functionalities. So, well, you know, it keeps on going. For example, let me tell you, the Largem precision compassing, which is a major cell phone lens supplier, produces about 15 billion plastic lens modules. Now, with the approach with Metalenses to dramatically compress this module, much less complex from the alignment point of view, okay, it's really, there is a potential for do some real technology displacement with meta optics. So this is just, I like to show this. You all know it, of course, but I'll still say it. I mean, the way you can think intuitively about a metasurface, it's of course an array of sub-wavelength spaced elements. You locally create wavelengths, and you can design these wavelets by designing these, which in a simplest way, they're just phase shifters. So they are tiny waveguides. And the key point really that took us a while to realize, in fact, I recently wrote with some collaborators this paper, it's dispersion in engineering is the key thing. Because it's a wavelength space, and because we can control the dimension of this pillar, we keep the same height. This can be thin, so we can control the various dimensions. We can locally control the effective index of these waveguides. So we can literally tailor the dispersion point by point in an arbitrary way. This is very powerful. This capability is not there in conventional Fresnel optics and in other types of diffractive optics as well. So you can design the wavefront, simply use Huygens-Fresnel principle. So once you've designed the phase map, you can you know actually what the wavefront here, and then you just do the simpler Fresnel-Sommerfeld integral, and you can see what the behavior is in the far field. This is the simplest case, which I want to show because you don't need any calculation. You just say, I want to make a diffraction limited metalenses, okay? So no spherical type of aberration with flat optics. So what do I need to do? So I populate this with my library of wavelength with different diameters. You can see here to the right, if you like, the phase distribution here. So I want to be able to change the phase to control the waveform, so 0 to 2 pi. So how do I have to phase the surface? Well, all the rays, the chief ray and all the peripheral rays have to arrive in phase here, and to have, so in order to constructively interfere. But this is not possible unless I phase the surface. Not possible because this length is different than this, so there is a phase shift. So the metasurface must compensate with this phasing here, fxy, the difference in phase between the chief ray here, focal length f, and any other ray. So you get this hyperbola here. This is a phase-only map. Okay, I am neglecting the effect that, of course, you can have different scattering amplitudes, so the efficiency can change with this. This is a factor, but with better design, you can actually include, take into account also the design of the scatter amplitude, and so increase the efficiency. So I just want to show you a bit, of course, it's the simplest case, but I want to really to show you now the flow of conventional metasurface design. So you get the target phase profile from analytical solution, or can be ray tracing, ZEMAX. Okay, most cases are related to geometric optics. Hologram is an exception here, which requires diffraction to obtain a target phase. I'm not going to go into it too, even though I'll show some holograms later. you build a nanostructure library by parameter sweep. Essentially, you solve Maxwell's equation by simulation software such as Numerical. And then you have to match the target phase with nanostructure phase, point by point, literally. You do your parameter, you have done your parameter sweeps, and then you try to get as close to the target phase with your meta atoms. Okay, so this is it. For example, the examples are a doublet, a typical, can also in an immersion lens. So I'll run through these briefly. Okay, you can do a Taylor expansion of the phase. You consider only the even terms, obviously, and the software tunes to actually minimize the figure of merit. And this is a distance between the target phase and the actual realized phase. So you start, for example, by giving a numerical aperture the field of view, okay, over which ones you want to have diffraction limited focusing. And then what Zemax does, it traces many of the rays, changes this coefficient to minimize the spread of crossing points, okay, on the actual image plane. So it's very simple. You have a circle, and the circle is of size of the diameter of the iris disk. And by this iterative process, you want to that all the intersection of the rays follow go in these circle. So then you have achieved diffraction limited performance. So that's the general idea. Now I don't have time to go here, but it's quite interesting. Available simulation packages. We use Numerical, but you can use other. These are other useful information. Now, this I don't need to add it to the chat. It's actually here. This is a website that one of my former researcher who now works for AMS has developed. It has very useful information on design. You can download codes here and so forth. And I really recommend it, and he's made it available for the general public. So now let me go. So let's start with the technology platform. We all know about e-beam lithography as our Center for Nanoscale System, which is a user facility. We have two e-beam systems, a high-speed writing, which allows us to use actually lenses as large as 2 centimeters in diameter. So it's not entirely fair to say that e-beam is only good for the actual laboratory. For a kind of more niche type of application, there are in fact companies that are starting to do meta optics by this fast e-beam type of lithography. We have also an ionic system here, which has higher acceleration voltage, so you have higher resolution, and this is really good for fine patterning and low proximity effect and so forth. So this is the process that was developed by my former graduate student Rob Devlin. This paper here is now the CEO of Metalens. Is our startup. This now is past the startup stage, and I'll say briefly something later here. But just quickly, this is a titanium dioxide-based metasurface. The message I'm sending, if we want to innovate at the device level, we want to use state-of-the-art fabrication technology, but materials that are state-of-the-art. We don't like necessarily to invent a new material unless it's absolutely necessary. So here for the visible, because it's totally transparent for all intents and purposes, we use titanium dioxide. This is a process that combines, as you can see, e-beam lithography. So it's a bottom-up fabrication here, and uses ILD, atomic layer deposition, to deposit monolayer by monolayer conformally on this pattern here. So you can see the process here. You build it up to a certain thickness here, which is about twice of the maximum feature side, because when you fill in, when you start to go, you fill in all these spaces here, then there is a chlorine etch thing, and at the end you have this other stuff. There are other materials that can be made with titanium dioxide. There is, for example, some other oxide, hafnium oxides, and so forth. Okay, what I want to draw to your attention is not only the negligible loss in the visible, you can make essentially perfectly vertical structures here. We use the same tallness, typically 600 nanometers here. We can control these width here. Now, of course, the tolerance here, there is some, 10, 20 meter variations that can be on the actual lateral size. And, but, these are random variations. So at the end of the day, remember, you are working at optical wavelength here. So the tolerances as far as fabrication are much less than they are for integrated circuits. Why? Because there you have to consider your tolerances compared to the electron wavelengths, right? The de Broglie wavelength, which is much less. So this fabrication technology is more forgiving in terms of tolerances compared to the same technology used for semiconductor manufacturing, in particular for ICs. So you can see here an example of the lateral, how close you can go. This is a berry phase metasurface and so forth, and we can do much more interesting stuff. In fact, in my group, people have started to make large area complex structure. They made, for example, a Metalens of 1.2 centimeter diameter. This is titanium dioxide on actually glass here, okay? And now there's also work going on complex shaped meta atoms for a variety of things, including, and this, of course, we use the higher voltage, the other system to get higher resolution. You want to minimize proximity effect. Here is an example lower, and this is where they started in my group in actual earnest. You can see freeform meta optics. So at the beginning, I was skeptical, but the progress has been so fast and the promise so great that I'm no doubt anymore. It's a matter of time. But it's in a 5 years period, meta optics with more conventional shape will start to become pervasive in a number of applications. In 10 years, you'll see real world application of freeform optics using inverse design, machine learning, all the power of AI. It's actually happening. It's going to happen. This gives you kind of a smorgasbord of the thing that my group is working on. We are working now on bilayer metasurface, where you see we have a composite meta atoms to the left here. In this case, we have a dioxide nanofins, a titanium dioxide filling matrix here. So this is, and you really have to understand and design this in a complex way, typically using an iterative process, including inverse design. These are some of the structures in particular that someone extremely capable in my group, Junsu Park, who has done top-notch type of fabrication. As you can see, these are the simplest one. And then we are moving here towards more complex one, and finally to freeform meta optics. So, the whole point is scalability for mass production. I wrote a paper with my student Alan Sheen and others, exactly pointing out that if you could demonstrate this could lead to the convergence of flat optics with the semiconductor industry and lead to the mass manufacturing of lenses. So we started with eye-line stepper lithography. Of course, the wavelength is reasonably high here. So we were able to do 2 centimeter diameter focusing lens, diffraction limited, infinity corrected with the stepper process using amorphous silicon, which is another platform technology. So this is one platform technology. Before it's titanium dioxide. Eventually, when it's going to be done by DPUE, and it's only a matter of time, it's going to become also a platform technology for mass manufacturing. Here you see simple glass lens, 1 centimeter diameter. Everything is glass here. 160 million nanostructure per lens. This is a detail here. And this we published, and we compared here our diffraction limited Metalens to a simple planar convex lens. Of course, here you can see the aberrations very clearly here. And simply because the rays that are peripheral focus in a different point than the rays that are close to the center. But then we compare it also to an aspheric lens, which should give you almost ideal behavior, diffraction limited. Well, the Metalens actually does quite a bit better compared to a commercial aspheric lens. Okay, I also want to mention other, this is other work. This was done by my group. This is work done, in fact, at A-Star in Singapore, using silicon, uses morphosilicon. And other technologies are in the making. In fact, we are working with 3M on roll-to-roll technology for large scale applications, and hopefully we're going to have soon a paper ready to be submitted. But there's also nano imprint also, and I will show you later some examples of that. So the scalability for mass production, I already said, is this convergence here. At the incubator meeting of Flat Optics, this was just before the COVID era starting, and there was a very nice convergence of industry, academia, and so forth. And this has led, in fact, this year to the first Flat Optics meeting, which will occur every 2 years. And our spin-off from Harvard, which is supported now by Intel, 3M, Applied Material, did a nice demo of a 2mm diameter metal lens on 12-inch silica wafer by CMOS foundry. So 10,000 lenses per thing, and I'll show you demonstration of an actual camera. What are the benefits? You see, the technology is inherently telecentric. So you don't have the fading of the intensity as you move away towards the edge of the sensor. The illumination is uniform. You get higher brightness compared to, in fact, plastic, and the simpler configuration, I think, and the alignment. The alignment is absolutely critical. We won't need those expensive machines to align things. Now, and this I want to stress because this is, I was authorized to show this very recently. In fact, this is Metalens. So you have the conventional, if you like, processing technology to do the deep UV. You enter, in this case, an optics design file. That's, of course, a key difference. But look at this. Now, this shows 12-inch wafer meta optics. This is amorphous silicon, okay? And then, you know, you can see what happens is there is a singulations, okay, where you can make thousands of these elements here, and then there is a back-in kind of integration to make the module. So Metalens has announced, this has been a product launch. It's called Orion. High-performance dot projectors used in mobile devices for face recognition and 3D sensing. This is just the beginning, in my opinion, of the flat optics revolution for high-volume markets. And you can look, it's all public in information at this website here. Now I want to take a step back to talk more about performance issue, because this is a tutorial after all. These are high NA metal lenses, infinity corrected. These are actually do not have the anisotropy like here, but they are simply circular pillar. They are designed for different RGB wavelengths. The diameter is about 2 millimeter. We didn't make any attempt to maximize the efficiency. I can only tell you that in the previous example that I gave, those high performance metal lenses in amorphous silicon by Metalens, the efficiency is now approaching 90% focusing efficiency. Of course, it's at a single wavelength. My message is there are already high volume application for single wavelengths, such as dot projectors in the near IR and so forth. When we published this paper, the science paper, we were contacted by Zeiss, who asked us, well, you know, we would like to look at your devices. You're welcome. They spent 2 weeks in my group, and we started a nice collaboration. In fact, there was a comparison between standard diffractive optical elements and metalenses. The main message is here, okay? The angular bandwidth over which you can have high efficiency is much larger for actually metalenses than it is for thing. And you can see it here from this color map here. Okay, this region, a far larger area than here. Now, people are saying, well, there are other technologies, so you could do, multi-level digital optics, like using grayscale lithography. I would say it's definitely interesting research, but there is a long way to go, because the limitation so far is this, that the big netting has been very significant so far. And the ability to get broadband, yes, it's there, but at a price of efficiency. In fact, you see the vignetting type of effect when you don't have the angular bandwidth. When you do multi-level optics, you see the fading away here due to the limited bandwidth. Whereas if you look at different type of metal lenses we did, this is one which is hit in particular with a bandwidth from blue to the green. And another example, you see that the vignetting, these are standard tools to test metal lenses like the Siemens Star or the Air Force standards. There is much less fading towards the edges. The Metalens doublet is a very interesting type of example of what you can do. You see, what you really are trying to do this, you are trying to correct coma, to have a large field of view and have diffraction limited over a large angle. So what you are trying to do is this, you see. What is really common, as you change the angle of incidence, the effect of spherical aberration becomes more significant. And so you have to correct the different foci for paraxial rays and the marginal rays, okay, for a certain field of view. So this is the strategy that we and other groups have used, is shown here. We have a focusing metal lens. And then what you really want to do with an aperture metal lens that uses, instead of a convex phase, as you go out here, uses a concave phase. What the concave phase does, it pushes the rays that want to be focused earlier or before towards the same focus. And if you do it right, lo and behold, you can have actually correct the third order aberration, spherical astigmatism and coma over a field of view of, plus or minus 30 degrees. To be careful because I'm losing my voice. So this is what you see here. And these are the results, the results by the Faron group at Caltech. You see, with a doublet, you can correct, you basically get diffraction limited performance over this angle. This is in the near infrared. We did it in the actual visible here. So it works pretty well. You correct also, of course, the field curvature. We don't worry about the distortion because you can do that by software. Now, this summarizes the work so far on achromatic. 2 groups simultaneously, my group and a group of Professor Dipin Tsai, then in Taiwan, he's in Hong Kong, managed to demonstrate a broadband metal lens, a broadband across the visible, okay, and infinity corrected. The physical idea is very simple. What I like to call this group velocity engineering. So you have, because you want to focus all the wavelengths in the same spot, you have to worry not only about the phase, but by the group delay. The delay, the derivative of the phase respect to frequency. What is that physically? There is an exact definition. It is the transit time of light in each nanofin. So you can engineer the group velocity here, so that then here you see is a short distance. You have to use fast light in these fins. As you move closer, you slow light effect. So if you do light at the end, And you have to actually take into account, because you are focusing a broad range of wavelengths in the same spot, not only the phase, but the group delay. And you have to make sure that the group delay dispersion is actually ideally zero. Okay, so the wave packets arrive in the same focus here with the same shape. This is at all wavelengths. That's the idea. Now, the difficulty of this, of course, is because you have to need a large range of group delay to compensate for these different paths. This strategy so far has been limited to relatively small diameter of the order of 100, maybe 150 micron. So we use a different approach. We say here, let's use the metasurface as a playmate of a conventional lens. So the idea is I have a refractive singlet. Here I put a metasurface. It's sort of the same principle as before with the doublet. Okay, this is designed, the phase, this is phase at different wavelengths. So for now you want to use it to correct the chromatic aberration. So in the blue, the phase is concave, so you push the ray forward in the same focus, but in the red, it's actually you push it back. And in the middle actually looks very much like a Schmidt plate. So this is kind of interesting. These are the results. In this way, we got a 1.5 millimeter diameter polarization insensitive focusing. So it is encouraging, very small to do. So Xiaoli in my group has taken the lead in thinking, can we make large lenses instead initially of achromatic broadband? Let's make achromatic for different wavelengths. So the idea here is very simple. I'll give you the physical idea and tell you briefly about the process. Using zone interference type of engineering, you have different zones here, okay? And each zone is designed so that it acts as an achromatic, yes, as an achromatic focusing surface. But then what you do is you want to essentially put different zones here. And then if different zones, now you have to engineer different things. And you do this actually by inverse design. And this is an optimization problem where you maximize the minimum of this so that you get the maximum in intensity at the desired focal point for certain design wavelengths. And the parameters here that you play around so that all these zones you see act constructively interfere. So you get first constructive interference within each zone. That you do by standard forward design. Then the constructive interference between the different zones, you go by inverse design, as I tried to explain here, where the key is the design of these phase discontinuities at different zones here. And it works pretty well. So I'll show you. So what you actually do is you create this library, okay? And then what you actually play in the design with this iteration, you play not only with the width, with the sizes here, but the orientation. And you see this is all by titanium dioxide, and it's pretty nice result. These were just published in Science Advances this year. These are the results for a numerical aperture of 0.3, diameter of 1 centimeter. You can see you get really diffraction limited, nice diffraction limited behavior as you look in the transverse plane for the 3 wavelengths. And also, if you look, we were able to minimize the multifoci here. And you have a nice trail ratio. So this is very encouraging. The same thing was done for 0.7. This is actually less demanding than 0.3 because larger numerical aperture. But basically, you can see the maximum focal shift is about 1 micron for this 0.1% of the focal length. And similar is 9.3. These are the results. So it's pretty nice. And with that, you know, we decided, well, this is not, of course, anything close to a commercial system, but the ideas of what you can do are quite interesting. To do a VR platform, this was done in collaboration with the Boston University. The idea is to have an RGB Metalens. You have a display here. You have your virtual image. And what you have really a fiber scanning near eye type of display. you see. So the light source uses a laser diode. The display features high resolution, high brightness, high contrast. By the way, you know, I should have said this. These ones here are actually polarization sensitive lenses that are designed for really focus well for right and left circularly polarized light. But of course, the next step is to do it, and we've actually done it. I just don't have time to show you the data. So you can ask, what's going on here? The light from the laser is actually innerly polarized, but what happens, you see, the right polarization is actually focused. The left polarization is actually diverging. So it really gives you just to increase background. So the effect is not detrimental in terms of the quality of the display. Again, this is a first prototype. In the future, I want to make everything polarization insensitive. These are the VR demos, you know, for intensity modulation. And again, and you can see here, we can also do continuous level intensity modulation. Okay, and you see you can get very interesting patterns here, even a Penrose diagram and so forth. So it shows really the potential of Metasurface technology for AR VR. I mean, that's the message. We also the VR and AR, you know, these are, you can get, you see the image of the design RGB color in the focus in the same place, okay, because of the achromatic focusing. This is a good display. You can get also grayscale full color image, and this is an AR demo. I just show you because it shows the potential of Metasurface. Now I want to go multifunctional Metasurfaces. Can we enclose multiple functions on a single Metasurface? Well, you know, yes, you are, and in particular, you know, we're interested the application in miniature spectrometer. Now, you can buy miniature spectrometers with high resolution, but you need really complex optics like toroidal grading, a spherical off-axis mirror. You actually name it. And so that you lose in terms of complexity. Even you find very good commercial products, but there is a difficulty of making. So we approached it differently, inspired by this. This, if you make it small, you just lose spectral resolution because you can't separate the wavelengths. That's pretty obvious. So how about miniaturizing? Well, this is the idea my group came up with, is to use an off-axis focusing Metalens. So as you change the wavelengths now by small amount, you get a large variation in the actual focusing. And so you can hope to get high spectral resolution by making a very compact thing. You are replacing, this is a multifunctionality. Essentially, you are replacing all these optics with just a metal lens, and you have the sensor. But there is a but, unfortunately. As you change wavelengths, the image moves on the sensor, this is a sensor, so then you lose a lot of your resolution because this point might be on the sensor, but not this, and so forth. So, you know, the beauty is when you have extremely smart students and postdoc, they come up with the actual solution. So Alex Zhu came up with this idea to use actually be able to essentially to eliminate the field curvature, that is a field curvature, and do achromatic focusing by designing this type of metasurface. By the way, I want to tell you that you can make polarization insensitive metasurfaces also with anisotropic structure. You have to use certain tricks, and we demonstrated this a couple of years ago, basically. This is if you don't do anything with dispersion engineer, or very little, that spot moves away from the surface of the camera. So you go to longer wavelength, it blurs. You lose a lot of your wavelength resolution. But if you now play this trick here, you correct the field curvature, lo and behold, you see, sorry, I should have pointed at this. Without dispersion engineer, you get a lot of blaring. I said it wrong. But when you do dispersion engineering and do this here, see what you get, a nice spot. And you can go down to basically less than a nanometer spectral resolution. Not yet, we have done the anterior visible. So I think this is a show of the kind of compact devices that you can do Now, the other interesting thing, you know, that we can use metasurfaces to implement multiple function. The most obvious is spatial multiplexing. Can be useful. We have done it, in fact, for chiral metalenses to do chiral imaging in biology and so forth. You can also do local metasurfaces based on matrix Fourier optics. Now, in this case, it's very interesting. You can design a metasurface with this powerful type of Fourier optics, okay, where each diffraction order essentially acts like a different analyzer. So you can measure the Stokes parameter if you use this as an actual polarimeter, okay? And but there is, see, all these approaches here use so far basically local unit cell, okay? And a local unit cell has certain disadvantages. So we use periodic boundary conditions. And so, you know, it's really good only this approach for normal incidence. So we're looking at small angles, and it undersamples large phase gratings connected to large deflection angles. Okay, this is one problem. And you neglect also the interelement coupling. So the non-locality means really to design super cells that include this non-local effect by having this element. An initial step for Metalens was taken by Steve Burns in my group in this, where he made an actual design Metalenses where he could focus on also for a large field of view, for a large angle here, by essentially doing a changing. You have this local grating here, where you actually change this local grating here, the periodicity locally as you move along, so you can now bend the rays equally well, not only at small angles, but at large angle. That's the idea, okay? And you can achieve a large deflection angle. And in general, you can, this is what we have been concentrating on local. And this is a paper, the results have just been published. And so the idea is now to do with this supercell to arrange so that each, if you like, this order implements a different function. In particular, it gets quite sophisticated. You can position your supercells on a curvilinear lattice, so you do not have to follow the phase fronts of the design, I mean the phase maps, right? And so with a sufficiently large library, this is the key idea, you can control independently each order so that different function can be created on each order, and you can achieve large diffraction angle with the same efficiency. That's absolutely key. I think here, these are actually data on a real metasurface where we went from angles over a range of essentially up to 50 degrees, minus 30 to up to 50, with comparable efficiency. The efficiency now, I forget the exact value, but it was ranging around, 30, possibly 40%. So we still have quite a lot to go, but you see different functionalities. Here you have a Bessel beam, here you have a Gaussian beam, here you have a beam with optical angular momentum, and it's quite exciting what you actually can do. Okay, we used it also, one of the most interesting applications, but I'm not going to tell you about it, that you can actually make a new external cavity laser where you do the wavelength tuning by translating the metasurface other than by rotating. In this case, I'm going to show you basically the basic principle here. The idea is to create an actual cavity where one order of diffraction is used to provide the optical feedback here, and the other order is to implement what function you want. Okay, there is a what vector beam. Here we wanted to create an actual hologram, the Harvard hologram, obviously, and the hologram design, projected on a CCD, the optical on a screen. Now, this is very exciting stuff that recently Mark Brongestad presented the first Flat Optics conference. I see I borrowed his Vuga, shows what you can do with active devices. So how can you make a metasurface-driven OLED with, you have 1,000 pixels per inch? Why can this be interesting? Well, it's very clearly how we can impact microcavity OLED design. Okay, the idea is, there are different approaches. You could use fabric cavity RGB OLEDs. And this is, you can use color filter, but here there is a complication. There is more bulk. The key idea is to use instead meta OLEDs that you can exploit the Purcell effect to enhance the light extraction. This is one effect. They can be designed to produce the desired refraction phase. You do not lose light in color filters. And you can use the planar. It's kind of really exciting. When I heard this, I said, wow, you can do a lot of stuff. So this is the spectral emission tuning typically of actually of this type of approach here, which I'm going to say more later. But basically, there is, of course, you have to put an anode, you have to put a cathode, okay, and you have to design your actually meta mirrors, and really that is the challenge. Okay, so you really design the meta mirrors for a particular color. So you design the reflection phase, okay, at the desired resonance wavelength. So this is a meta OLED, and this explains a bit better physically how you get the full control here. You see, when you do the phase, normally you just, like in a Fabry-Perot, is a propagation phase and the reflection, and the reflection phase. Here you can literally design this refraction phase any way you want and optimize it for the wavelengths, make this compact. In fact, this original concept was tried first by Vlad Shalaev and his group in a NatureCom a few years ago. So really, you can engineer the phase based on what you need to do. And the process they use, in fact, finally, I can show you the nano imprint type of lithography. So there are indeed application of this lithography technology for metasurfaces. And this is the color gamut. This is really, I think, quite exciting, the large color gamut that we're able to achieve. This is now the electroluminescence, okay, the solid OLEDs, the color. And and this shows the actual luminescence as a function of current density. The key point is you've got comparable performance in terms of current density and light for the three colors. So I'm quite excited about this. I'm now close to, getting in the last part of the talk is about cameras. I thought I gave you the message, you can make, you can take existing cameras and make them much better, more functional for a number of applications. It could be depth sensing, face recognition, and so forth, replacing existing technology. Can you use kind of novel design on metasurface to do something a bit different? Now, of course, depth sensing cameras have been for a while. So here, the idea came actually from my former student. She works for now Apple, Zujun Shi, with in conjunction with Todd Ziegler Group, who are experts in computational imaging. The basic idea of depth cameras are well known. They've been around for years. Here, they took clue from the spider. The jumping spider precisely captured the actual page, so it has a good depth map. It almost never misses. If you put it in blue light, however, rather than green, it starts to miss. There have been fascinating experiments there. So the key idea, how does this tiny brain do it efficiently? So it obviously is a combination of hardware, but the neuron circuits means there is some interesting software that we don't know, and biologists and neurobiologists of these animals haven't figured out. But my people took clue with Todd Ziegler of this, and they said, well, we know how these lenses are. There are two essentially transparent, semi-transparent retinae. Each produce a different defocused image, defocused. And from the amount of defocusing, you can actually get the depth map. We don't know exactly how the spider does, the jumping spider, but this has been the design thing. Why is this important? Depth cameras right now are very computationally intense. They need typically a cluster or maybe a fancy GPU. So can we achieve lower power computation somehow by introducing the calculational aspect, the software part, together with the Metasurface, sort of under-design the Metasurface, if you like, or design it in a way to try to do what these retina do, but in a single plane, and then use so again, this is the idea. Of course, we can't quite do this because this is not quite cumbersome to do it with two Metasurfaces. Let us do one spatial multiplexing. So this Metalens produces two images with different amount of defocus on the actual sensor. So point by point, you have an intensity map. And there is a very simple algorithm that our computational imaging friends in Todd Zickler group figured out, where by taking essentially, I'll show you how mathematics is done, you can derive the depth map. You essentially know if you're looking at fruit flies, at what depth they are, right? And so that's what the Metasurface does. And so depth from the focus, the depth map, the reconstructive type of equation is very qualitatively easy to understand. Alpha and beta depends on the design of the Metasurface. Delta I is a difference in intensity pixel by actual pixel. This I is the sum of these two here. So you can actually compute point by point from the images, this delta I and the Laplacian. So this has led, I'm talking here not as an expert. Fortunately, I have great collaborators who are the expert. Greatly reduce the computational burden 10 times less than a typical light field depth sensor, high speed, 150 frames per second. So this is a promising, we think, for micro robots, for drones, whether you have to lighten the computational burden. Plus, you have the flat optics because you have very little space in micro robots and also in drones. So you will see the results here, particularly for moving objects. They are fascinating. The range is so far only 30, 40 centimeters, but we are working, my people, to increase the range to meters. And you can see the reconstruct. This is this paper here, now 2 years old. And I want to show you the first movie here, the water stream. So left and middle, the two images here, the reconstructed depth map with the color code. These are meters, okay? And then the candle flames. Now, there's absolutely no way to do this stuff with actually time of flight. That should be pretty obvious, right? Fruit flies, also quite interesting. So I think it's very powerful for moving object. Again, we are at the beginning here of a really new direction of co-designing the computational part and the hardware part to lighten the burden on the design, but then speed up, the rest by. So the next thing is, I really want to tell you, and I don't have a lot of time, I realize, but I'm going to finish in time. How about seeing polarization? Now, of course, this is important for science, but increasingly for technology. For example, this is a beautiful early work on the left side here, where my cursor is, by Nader and Gator's group, where by looking at cross-polarize this scene, they were able to detect a hidden tank, okay? They might be important for autonomous vehicles, for the state of the road and so forth. And for 3D machine vision also important. You want to make high quality paths, minimizing roughness. So polarization can be very good in seeing with high detail roughness. Security also, you might say, my cell phone, my Samsung is extremely secure. Not entirely. You can fool it. The chance is very small, of course, with a flat image. But now if you have a polarization sensitive thing, there's no way, because polarization gives you depth. There's really no way, almost no way, to fool it with a flat image. The hero of this work now, it was my former graduate student. He's now a postdoc, and he leads an effort to put this new polarization sensitive camera in the stratosphere. We are working on 2 NASA programs in atmospheric science and in astrophysics. I won't have time to talk about it. So there is a large space of application for meta optics in science. So the standard techniques are, well, you know, you have to measure the Stokes parameter of light point by point. And we know from theory, the Stokes parameter, you need 4 intensity measurements, right? So the way if you do division of time, you have to essentially rotate your retarder here, your polarization optics, so that you get different intensity image for different polarization. You combine them together, and this gives you the Stokes parameter point by point, which means the polarization image. You can say, I don't want to do that. I want to do division of absolute. I want to send light in different paths with different polarization optics, combine the images. That works. But, you know, there are minuses here. Finally, you can do brilliant solution, Sony, focal plane, division of focal plane. There is, the fabrication is not easy. Of course, it's quite expensive. And it's only good for linear polarizations. We are interested for science in circular polarization. So we've asked the question, can we have a single metasurface replace all this componentry? The answer is yes. So it's to go well beyond the traditional polarization optics. And if you science do polarization optics without traditional polarization optics, so we use these metasurfaces that locally we can control the polarization, right? And then the Stokes formalism I already mentioned. We need essentially 4 intensity measurements to analyze the polarization of a source, and I mean a source which has arbitrary polarization, including partial polarization. So once you have co-register your images at the 4 intensity, you can actually get from the Stokes vector, you can get the azimuth, the ellipticity, and even the degree of polarization. And the azimuth really tells you a lot about the surface. So this is a general idea. I'm compressing the work of this 30-page article in Science. I mean, the text was not 30 pages, but the supplemental is 20 times longer than the main text, where we introduce a powerful generalization of matrix optics. I really have to encourage the father of Fourier, to thank the encourager, the father of Fourier optics, Joe Goodman, because when Noah and I started to talk about this stuff, we went to visit him at actually Google, and he gave us a strong encouragement to go in this direction here. So the idea is we have a metasurface grading, because of course we have multiple diffraction order with a unit cell. And what this does, it creates different diffraction orders, which acts like analyzer, literally analyzer, that are for different polarization. So you can simultaneously analyze the polarization of the source, including partial polarization, in different directions in space, which are different diffraction. They act like analyze. Are they really analyzer? Sure they are. They are not, of course, they do not based on absorption. So lights get shuffled around when you change the incident polarization. So let's say if you hit it one order with this polarization, you get maximum intensity. You go perpendicular polarization, you get a minimum. You don't do as well as a polarizer, but it doesn't matter, in fact, for what we want to do. So then you get these images in the 4 corners, and you co-register, and lo and behold, you can get actually point by point the polarization of the scene. These are the things we use: optical optimal polarimetry, using a tetrahedron to put the analyzer states on the vertex here. So this corresponds to different in space. This shows the actual unit cell. This is optimized for the green. The contrast is plenty for more than 90% for what we need to do here. There is good agreement between simulation and measurements. You know, it has to be so large only because my student and postdoc have to put their hands in it. And once I did it myself too, but you can make it much more compact. What's the advantage? No moving part, no polarization optics, just metasurfaces. It's inexpensive, detector limited resolution, full weight imaging. Is it all so good? No. The challenge is, of course, to make this multiple wavelengths achromatic. That's a big challenge. Fortunately, there are many applications. Like if you want to look at the quality of a surface, you don't need to use broadband. Many atmospheric science applications, including solar physics, we are just thinking about, you know, individual wavelengths. So this is the metasurface. Again, think of it as a metasurface. This is just gold here to avoid, you know, the background, and the metasurface, the metalens. So what does the camera see? 4 images, okay? They must be co-registered, and this is the 0th order background. You can, of course, put how could you solve in part? Well, you could put, you know, a phase grating and sort of go at a different angle, so you can actually decide to minimize if it bothers you. It's 0th order. This is typically what these raw exposures get. You see the intensity, the CS0. You can get the azimuth, and you can get the degree of polarization. It's time to conclude with the actual movies. I'm showing you the real-time polarization feed. You see here there is actually a car. Look at the azimuth. As it's turning, I see more reflection because the polarization depends, of course, of reflected light on the actual angle. And so you can see visually the power of this technique here. You have the image in real time of the degree of polarization. Here you turn the wheels of the polarizer, and again, watch at the azimuth here, okay? You see, you actually changing the actual color. It indicates you have a variation of the direction of the polarizer, and you can see that from the azimuth image. This is the most exciting because it shows you the depth. We are rotating an actual bottle. By the way, what's the background light? It is an LED with a diffuse light. It comes from all directions. You see, as you rotate it now, because of the variation of the reflection coefficient with angle, of course, the polarization changes, and you see this effect very, very beautifully, the depth. If I didn't show you that, you just showed you this here head on, you know, you'll say this could be a wheel. Why does it have to be a bottle? Only if you look at head on, you'll think, if you look at a different angle, you'll see that it's actually an actual bottle. Stress induced by refringer. Here we took light from a LCD screen, which is polarized, and we let it go through pieces of acrylic, and we stressed it. So now as we stress it, you see again here the map of the birefringent by looking at the actual azimuth. And even here, you know, a tape, this dispenser has built-in polarization. So it's time to conclude. I hope I've given you a tutorial on the essential method approaches of flat optics, and also the promise for real-world impact in technology for high volume. I don't have really to say much more than this. You know, there's, as you've seen, tons of people that have contributed to this. I mean, over 50 total. And I want to, in particular, thank the funding agencies that are DARPA, the Air Force Office of Scientific Research, NSF, and lately the Office of Naval Research. And all the fabrication was done in our Center for Nanoscale CNS system with us, which is a user facility incidentally. For those of you that are in the United States, it is a user facility. You can apply for actually time. Of course, things cost, but they also cost for me that I am at Harvard. So with that, I thank you, and I'm glad to answer some questions. Thank you very much. Bye. So are there any questions? So I hope you can hear me, but I don't see any questions in the actual chat. I'm just going to stay here for a few more minutes, okay? Okay, here's a question. Yes, folks, thank you. I'm wondering how long it takes to fabricate a wafer scale Metalens array. Well, I'm getting into details here, and I've been told strictly on to idea, but I would say, you know, it's no different and in fact simpler than an IC chip, okay, at this stage, you know, so that's all what I can say. Can you collimate the beam using the same Metalens? This is a very interesting question. You know, how I started flat optics is this. I was working with a leading atmospheric scientist. He's here at Harvard, Professor Jim Anderson, who created the Montreal protocol for the ozone hole. And he was sending my quantum cascade laser in the actual stratosphere in planes. And one day he says, I want to put these in drones. I don't have space for the lens. So can you eliminate the lens? And I said kindly, this sounds crazy to me. We'll think about it. So I talked to Nanfang Yu, who's now a professor at Columbia. We squeezed our brains together and we said, aha, we need to make a contact lens for the quantum cascade laser. So we could call this, yes, a metasurface collimator that was able to reduce the divergence of the quantum cascade laser from plus or minus 30 degrees down to a few degrees. And that was really quite exciting. So that in sense, I was sure you can actually do collimators. In fact, you can do projectors, you know, and you can combine lenses in different ways. The key is at the end, you try to compactify this function as much as you can, if you can use just one or two, you know. Yeah, more questions, please. I see that they're finally coming. I'm going to stay on for another 5 minutes, and then if you have a question that comes after, feel free to email me and I'll try to answer them. Well, oh, yes. Well, sorry, maybe I went fast. This is a question. Non-conventional, like nano imprint lithography for the fabrication of metal lenses. There is ongoing work, but I showed you definitely an application, potentially for high volume for OLEDs, nano imprint, to make actually these wavelength selective elements, right? So definitely So if it can be done for that, it can be. I don't see any problems actually for nano imprint. At the end, I am a very pragmatic person. I would say, tell me what the application is. The application tells you what is the most effective technology. For lenses, definitely it's going to be deep UV, in the future, extreme UV. And extreme UV gets very interesting, the shortest wavelengths. Now, in my group, we are exploring ways to make metalenses for the extreme UV down to, wavelengths less than 100 nanometer. It's a long process. We are quite excited about the possibilities. So I would say, yes, the technology applications are very important, but equally important, they are the basic science one. And I think in both areas, we just start to scratch the surface. So, folks, I'll say one last question, and then probably I will leave. I will count till 20 or 30, and then hit the leave button. I need to go and have my lunch. I want to thank you all for staying. And so I don't see anyone. I'm down to a count of 8, 7, 6, 5, 3, 4, 2, 1. Okay, bye, folks. Have a very good conference. Thank you.